Apologies for the technical difficulties we were just having, but we are here.
We got knocked off of YouTube. So what we're going to do is we're just going to continue on with our show. So Dave?
Yes, I think I have the first demo right over here. Let's come on over. And what we're going to do is we're going to explain Newton's first law using this setup I have right here. All of these objects on this tablecloth actually have mass. That means they need to follow Newton's first law, which is the law of inertia. So they will not move unless a force acts on them, and they won't stop their motion unless a force acts on them to stop their motion. Well, you can see right now they're not moving, and you know there's romance in physics, so I'm actually going to light this candle right here, because why not? And you can see they all sit there without moving at all, because of course no force is acting on them except maybe the force of gravity, right, holding them to the table. But I can pull slowly on this tablecloth and it actually brings them towards me, because there's a frictional force between all those objects and the tablecloth, and that means that they've moved due to that force. But what I can also do with this tablecloth, instead of pulling it slowly, I can change that parameter. I can pull very quickly on this tablecloth. That actually overcomes that static force of friction that's on all these objects. So there's no longer any force on those objects, so they should just stay right there while I pull this tablecloth out from underneath. And, you know, science is everywhere, but magic also uses physics quite a bit. So let's see if we can use a little physics to show something that looks like magic. 3, 2, 1, and they stay there without any problem whatsoever. So that's our very first demonstration. So now we'll move to our second demonstration. Thank you, Borislav. Over here, that will go.
So here, as you can see, I have a series of bowling balls here. And right here we have a 7-kilogram bowling ball. It's quite heavy. And here we have a 3-kilogram bowling ball, much lighter. And what I'm going to do is I'm going to fill these two containers with water. We're going to do a little bit of exploration. So here's my bucket of water. So let's take this first bowling ball, the 7-kilogram bowling ball, and I'm going to lower it into the water. And what do you expect will happen? Let's find out. As you can see, the bowling ball sinks. And you probably am thinking that, well, that makes sense. Bowling balls are heavy. They should sink in water. Well, what about this bowling ball? This is a 3-kilogram bowling ball. It floats. Why does it float? Well, if you think about it, when you bowl, not everybody can lift up a 7-kilogram bowling ball. Perhaps an adult can, but a child may need to have a lighter bowling ball. So how do we make that happen? Well, it has to do with the materials inside the bowling ball. See, bowling balls have a center which is made out of cement. And the large bowling ball has a lot of cement inside, where the lighter bowling ball has less cement inside. So the difference here has to do with density. The greater the density, the higher the chance that the bowling ball will sink in the water. So let's walk over to the counter in the back. Follow me. And what we're going to do is we're going to explore the density of gases, as well as the properties of gases. So Dave, what do we have here?
Well, I have a balloon for you right here. This is actually a helium balloon, and I'm going to tie this shut for you.
Okay.
So there's our helium balloon.
Okay. And helium, we got that out of our helium tank right here.
That's right.
Okay, what do you have there?
I have another gas in here, and this is actually sulfur hexafluoride. So the density of helium is actually less than the density of our surrounding air.
So if I let go of the balloon,
it should float right to the...
It floats right up.
Right.
Okay, that's exactly what it does.
Exactly. Whereas this gas is actually more dense than the surrounding gas that we have in the air. So if I let it go, and then it just goes ahead and falls right down and hits that table.
That looks like it fell just like regular air. So let's test it against regular air. So here's a balloon. Now, there's air in the room. And when I breathe it in, I'm going to use a little bit of the oxygen, but most of the air that comes out of my lungs is going to be composed of nitrogen gas and the same air.
Yeah.
About the same size?
Same size, yep.
Okay, tie that off.
Fantastic.
And what we'll do is we'll compare that balloon to something that we understand.
That's right.
Okay?
We've seen this before.
So this will be our control. Okay, ready? 1, 2, 3.
And you can see that this does fall very nicely through that air. It's just more dense.
Let's do that again, a little higher. 1, 2, 3. Okay, so that just kind of crashes down. Okay, it's much denser. So I'm going to fill another balloon full of helium gas, and we're going to have a little bit of fun with this. Dave is filling up the other gas. Okay, so what's interesting about helium is an inert gas. It doesn't react with anything. Now, I don't want you to try this at home. We're professionally trained, and we know how to do this demonstration, and we also know what to do if something goes wrong. So please, don't do this at home. I'm going to take this helium gas, and I'm going to breathe it in.
And you notice that my voice changes. Now, why does my voice change?
Well, I think the density is lower than the density of the gas that's usually used to create that vocal sounds. So your voice box actually is creating a higher pitched vocal sound due to the helium inside your body. Yes.
Exactly. And if you notice that as Dave was talking, I was heavily breathing that, pushing that helium out of my lungs, is because if there's no helium in my lungs, there's no air in my lungs, I'm not going to be able to survive. That's not good. Yeah.
But as we saw before when we had this balloon dropping onto the bars, we actually have a more dense gas here. So ask yourself what might happen if Dave breathes in this sulfur hexafluoride. Well, let's find out, right? That's how we actually learn. We do the experiment. That's right. My voice now gets much deeper. But the problem with this is gas is the helium molecule actually leave Barstow's body, whereas the sulfur hexafluoride really doesn't. So I have to really work to push it out of my body so I can actually breathe once more. And those are the densities of gases in comparison to each other. So our next demonstration.
Let's do the balloon demonstration.
Inside, yeah. Now what do we have inside this small styrofoam doer?
So we have something which is called liquid nitrogen. Larry, could you show the liquid nitrogen over here? Could you come in over? So the liquid nitrogen kind of looks like water. The difference is this liquid has a temperature of minus 196 degrees Celsius. It's really, really cold. So I don't want to put my fingers in there, but what I will do is I will take a flower and I'll immerse it in it, and we'll find out what happens to the flower. And you see that the liquid nitrogen is boiling, and the reason is because this flower is about 200 degrees hotter. And that's boiling nitrogen. So it's not boiling water, it's boiling nitrogen. And that's the nitrogen changing over into a gas. So that's probably enough. And so now what we have is all the water in the flour has frozen. So I can take that and break it apart.
Amazing.
Okay? So certainly I don't want to put my fingers inside that liquid nitrogen because the same thing would happen to my fingers.
Not a good idea.
So here you can see that we have another balloon full of a gas which is lighter than air. This could be helium, it could be hydrogen even, because hydrogen gas is also lighter than air. What I'm going to do with this is I'm going to take this and immerse the gas into the liquid nitrogen.
That's it. Roll. Roll. There you go. Keep rolling. Keep rolling. Keep rolling. That's it. Keep rolling. That's it. So we're taking the energy out of the helium that was actually inside that balloon. By taking the energy out of the helium, it no longer pushes on the skin of the balloon from the inside with such force. So you actually are, by taking the energy out, the kinetic energy out, you're basically letting that balloon now shrink. It's not pushing as much, but it's the same amount of helium, which means we actually have a more dense balloon than we did before. By changing the density, we now have a helium balloon which should no longer float.
So what would happen if I take this out?
It should actually just fall off the table and then re-expand. Yeah, right like that. So it's a helium balloon that no longer floats, but you can see that energy re-enter the helium as it's sitting here in our warmer atmosphere, and as that helium starts to expand, well, sooner or later, and hopefully sooner, give it a little push, it will now lift itself right back up, and it's back to being a very happy balloon.
So that's the effect of temperature on gases. If you take a gas and you cool it down, it contracts, it gets cooler.
That's right.
And takes up less space.
But here we have some more liquid nitrogen, and if I just take this liquid nitrogen, you'll note if I pour it out onto the table, it immediately expands into that gas once more. And it actually takes up 800 times the space from a liquid of nitrogen to the gas of nitrogen. Well, let's see if we can use that energy. Because what I have over here is an aluminum tube, and it only has one opening. If I pour that liquid nitrogen into this tube, you can see the steam of the nitrogen pouring out the top of the tube as it expands again. But let's use that energy. And how do we use that energy? Well, if I go ahead and take a cork, it will actually pop that cork straight into the air, just like a rocket. Let's do a second one. Whoop, whoop, whoop. Just like that, and I can fire that cork right over that way. You can see just how much energy happens from the expansion. But we can do this with a whole other device. What we have over here is a cart. Borisław, would you like to wheel that cart back over to here? Thank you, sir. And inside this cart, we have ourselves a fire extinguisher filled with CO2. There's a whole lot of energy inside all that CO2, which is inside the cylinder. And I'm going to take all that energy of that CO2 and I'm going to hit the sail that's on that cart right there. Now, Newton's third law tells me that every action has an equal and opposite reaction. So what I'd like you to do is actually ask yourself, well, Dave, what happens if you go ahead and hit that sail with all the energy of that fire extinguisher? Which way does this cart actually move? And I say we should do the experiment right now with that. So ask yourself, do we move that way when I do the experiment? Do we move that way when I do the experiment? Do we move this way when we do the experiment? Probably not. How about that way when we do the experiment? Well, probably not too. But let's find out what direction this cart's then going to go in. So I'm going to sit right here. I'm going to go ahead and pull that little key out of the fire extinguisher. And now what I'll do is release all that energy into that sail. Let's see what direction I move in. 3, 2, 1. Well, it turns out I actually don't move at all. And why is that? Well, that sail is attached to my fire extinguisher. So we basically have no net force outside of our system. But Borisław is going to actually help us right now. He's going to go ahead and take that sail off. And if you ask yourself, well, what direction will this cart now move in? I think it's fairly obvious. We're going to rock it forward this way. But remember, Borisław's right behind me with that sail. He's going to feel all the force of this fire extinguisher as I rock it forward, and he stays right there. I would get behind me a little bit more. I would go a little bit more. That's it. 3, 2, 1. So that's our rocket cart. That is fun. All right. So that's in moving gases, and we have gas all around us. Right? As we've been discussing, we have our atmosphere all around us, which is basically made out of nitrogen, and there's lots of other gases. In New Jersey, there's actually a whole lot of different gases. But here, I have this long tube, and it's filled with that same air that's all around us. Well, we're going to use now that force of air to show you a really fun demonstration. Well, how to do that? Well, in science, what we sometimes do is we actually take things away in order to understand them. So let's take out all the air from this tube, and I'm going to do it with this vacuum pump right here. Now, all the air is now leaving this very long tube. And once all the air is actually left all that tube, well, what I have inside this tube, on one side, way over there, is a ping pong ball. Very light and fluffy piece of plastic. Not much to it. It's sitting right there inside the tube. On the other side of this very long tube, I actually have 3 soda cans. And you can see them right here inside this box. 1, 2, and 3. And soda cans are made of metal, a little more strong and rigid than actually that ping pong ball. But hey, when I now use this hunting arrow, and what I'm going to do is actually go ahead and poke the end of the tube right here. In doing so, the same force of air that's pressing down on all of us right now, that same force is going to re-enter the tube on this side. Force is equal to mass times acceleration. The mass of the ping pong ball will then accelerate down that tube. And when it leaves that side of the tube, it will be going faster than 1,000 kilometers an hour. Very fast indeed. So let's see what happens to our soda cans. 3, 2, 1. Let's go through our experiment. I hope you enjoyed that. That's always a lot of fun, especially when it works right. And here is can number 1, shot through with a 1,000 kilometer an hour ping pong ball. But here, can number 2, shot through by just a ping pong ball. And here we have can number 3, totally destroyed, and actually a great big hole in it from giving birth to a ping pong ball pieces. So that's the force of our atmosphere. We can actually propel a ping pong ball with that force up to 1,000 kilometers an hour. Oh, we seem to have another demo over here. That's non-moving air, but here I can actually have a device that can move air. Now, how do I prove that to you? Well, you shouldn't just believe me when I say, okay, I got this device that can move air. Let's see if I can show you that it actually does move air. And how to do that, well, Borslow has a candle, a torch to light the candle. And one of the ways we use air in our breath is we actually can blow out candles. So if I take this device, I can blow that candle out. You probably saw Borslaw's shirt move a little bit. So now you can all believe me when I tell you that this device actually moves air. But what scientists really love to do more than anything else is really show what's happening. We don't just want to show the effect it has on something, but we want to see exactly what's happening with this air. So let's do that. We're going to use a fogger over here. I'm actually going to put fog, theatrical fog, into our cannon. Filling it up. And theatrical fog is just glycerin. It's about the same density of air, so we can now see the stream of what's happening. If I go ahead and shoot this now, you'll note we have some very nice smoke rings coming right towards you right now. And you'll see that's actually the shape of what we were doing before, but now we can actually see it, which is one of the reasons why science is so much fun. But hey, what's that shape we have on our cannon? Well, that's a circle. What's that shape we have on this piece of board? Well, this is actually a square. So if we take the square, we put it right here on the front of our garbage cannon. Well, ask yourself, what shape will we see when I do this demonstration again? And, it's a really fun question. And I've had a lot of people talk about this. Will we get smoke squares? So ask yourself, will we get smoke squares? Well, let's do the experiment and find out. And if I go ahead and shoot them now, you'll know it's still a smoke ring. There really aren't any smoke squares that you'll get in nature or even in a science experiment, because the only stable shape is that smoke ring. And that's what we get with moving air too. So that's right down here. And, oh boy.
Good. We ready?
This is right over here, right?
Yep.
So now we're going to talk a little bit about pressure and force, but we're going to do it in a very unusual way. And we're going to take this pretty large bed of nails and put it right down here on the floor in front of our garage. And I'm going to take my body and I'm going to lie it down on top of this board. And these are real nails. I know, because I built this. There we go.
How's that feel, Dave?
Well, it feels like a lot of nails.
A little bit of acupuncture going
A
on?
little bit of acupuncture, yeah.
Okay, so Larry, could you help me over here? What we're going to do is we're going to take a second bed of nails, a covering, a blanket.
Every bed needs a blanket. Mine just happens to be another bed of nails.
And we're going to put that right on top. We're going to drop that right on top of it. Is that good?
Yeah, fantastic.
Your leg's good?
Yeah, I'm good. Okay. All right. Now I'm lying between two beds of nails. And to show you how effective this can actually be by having all these beds of all these nails on the nail board, well, Borislow is actually now going to step on me.
Are you sure?
I'm sure.
No juices are going to come out.
No juices are going to come out.
Okay.
I hope not.
The blue or the red? What do you think?
Whatever you think.
Okay.
You good?
I'm good.
That's it. So now I have the master Borislow on me while I lay between two beds of nails. And I'm not yet quite screaming in pain, although Borislow is not the lightest person in the world.
Let me jump off?
No, let me get down now. Thank you so very much. Fantastic.
So Larry's going to help me put this back.
All right.
Okay. You okay?
Oh, all good.
I see pinpricks on your pants over there.
Wouldn't be surprised. But right now we have another effective way to show you just how interesting this demonstration is, because what we have first is a shield that looks somewhat like a guillotine. And I'm going to put it right here on my neck to keep myself safe. And the next part of our demonstration is actually a cinder block, which Borislow is going to stick right here on my rock-hard ass.
Is this good?
That's fantastic.
Okay.
Oh, turn it the other way. Turn it this
This way. Okay. Good.
There we go.
Okay.
All right. Now,
Okay.
Borislow has a last part of our demonstration. And for that, we
5
have
kilogram.
a sledgehammer.
5 kilogram sledgehammer. And what we're going to do is we're going to apply a little bit of pressure to Dave, but we're going to apply that pressure to Dave through the brick, and we're going to see what's going to happen. Are you ready?
All set.
Okay. 1, 2, 3.
We can actually bust the brick while allowing the nails. And this board has kept me safe from any of the shards of the brick. But you'll know I am perfectly fine. I'm not screaming in pain. I don't have any broken ribs. I might have a few rips in my clothing, but that's really it. And that's our bed of nails demonstration. Put this back over here. There we go. Let me set this up right here.
So what we're going to do is we're going to explore what just happened, and this will be our model of Dave. Why is it that Dave was able to survive the bed of nails? So let's walk over here. And what we have is a series of nails. And let's start off with this one. This is where Dave was lying. And if this is our Dave right here, our model. So Dave could actually lie on this bed of nails because of the concentration of the nails here. So Dave weighs about 100 kilograms. And that bed of nails has about 1,000 nails in it. So that means there are 10 nails supporting every kilogram of mass of Dave's body. But this bed right here has a lower concentration of nails. There's only about 100 nails here. So that means that 1 kilogram is supported by 1 nail. Now, that's still okay, but it would be real prickly for Dave. This one here has a distribution of about 10 nails. So that would mean that 1 nail supporting 10 kilograms. So, but you see that we'll be able to survive that. Be interesting. Well, what would happen if we put Dave on a single nail? Well, of course, that would fall. So that's talking about pressure, force per unit area. Dave's weight was distributed over 1,000 nails, which is why that demonstration works. Dave, what's next on our agenda?
So we have another demonstration right over here. And this time we're going to shift to a little bit of chemistry.
Ah, okay.
I think you need to get your gloves on too before.
Yeah, so what I'm going to do for this demonstration, because it involves a pretty volatile chemical, I'm going to put on a pair of gloves and goggles. So what I have here in the brown bottle is hydrogen peroxide.
Hydrogen, is it regular hydrogen peroxide?
Well, this is household hydrogen peroxide right here.
Okay.
And hydrogen peroxide, do you know what we use it for?
Sometimes when you get a cut, you want to kind of clean that cut out. I'll pour that on. I see the peculiar effect. There's like bubbles that happen when
bubbles happen, exactly, and that's what I want to explore.
Okay.
You see the blood in that cut. I actually have a cut right here. I cut myself a couple days ago, and when I poured hydrogen peroxide, it started to foam. That's oxygen. So what happens is the blood acts as a catalyst.
I see.
And causes the hydrogen peroxide to turn into water and oxygen bubbles. And those oxygen bubbles is what actually causes a disinfection. And kills any bacteria in that region. Yeah. Here I have 30% hydrogen peroxide. So this is 10 times the strength of this. And thank you. I'm going to have to protect my eyes for this one. So what we're going to do is we're going to have a little bit of fun. And I'm going to tell you a story of a friend of mine, and his name is John of Montana.
John of Montana.
And John of Montana worked in a zoo. And you know what he did in the zoo?
What did he do in the zoo, Warsaw?
He brushed the teeth of the elephants.
Oh, no.
And now when you brush the teeth of the elephants, you're going to need to have a lot of toothpaste on that toothbrush.
Yeah.
So I made some elephant toothpaste for him, and we're going to make elephant toothpaste together right now. So it's going to start off with concentrated hydrogen peroxide, 30%, and what we're going to do is I'm going to give you the flavoring agent.
Thank you.
And I will put in some soap because you have to have some sort of a detergent to clean those
teeth. Those are big teeth, right?
So put in that detergent right there.
Okay, so that's just hydrogen peroxide and soap that we have right now.
And here I have some green food coloring. So that'll be maybe our mint flavoring.
Yeah,
so
why not? Can they do the whole bottle?
The whole bottle.
The whole bottle.
That's good. And I'll take that.
You got it.
And once you give that a little swirl to mix that in, and just like the blood acted as the catalyst to produce those bubbles on the cut, what I have here is I have a solution of a catalyst. You're going to dump this catalyst
Fantastic.
all at once, quickly, and then stand back.
Oh, okay.
Okay?
I have to move back very quickly.
You have to stand back safe.
I'm not in any danger here, am I?
Well, that's why we have gloves.
All
and that's why we have the goggles.
When we do these experiments, let's find out what happens. 3, 2, 1. Right inside. Oh my goodness. We have quite a lot of toothpaste for that elephant. Is this what John does all the time? All the time. It's too bad we don't have an elephant to clean his teeth because we have enough toothpaste for it. It's steaming also. Is there a lot of heat being used?
It's a very exothermic reaction. So there's a lot of energy released during that reaction.
Okay.
And that's why we're wearing the gloves and wearing the goggles.
Making sure our safety is important. Absolutely.
Exactly. Okay, so why don't I clean this up? You take care of that. I'll do the next demo. So this next demonstration, we call this dragon's breath, and it illustrates how powerful chemicals can be. And it also illustrates the concept of safety. So what I have here is I have spores from a mushroom. This is called lycopodium powder. And lycopodium powder are spores of a mushroom. And spores are very, very dry. They don't like water. They're hydrophobic. And because they're also very, very small and hydrophobic, they're also very flammable. And small particulates are very easy to burn. So what I'm going to do is I'm going to light this candle for you. And I'm going to take some of this lycopodium powder and put it into this funnel. So you see it pours very easily. And I'm going to blow the lycopodium through the candle flame, actually just above the candle flame. And let's see what's going to happen. Ready? 1, 2, 3. So that shows the volatility of fine, tiny particles. And this brings us to our final demo.
I just got the water on though.
Okay, water's going away. So I'm just going to put this into position. And we need to do a little bit of setup here for this final demonstration. And we're going to be working with liquid nitrogen again, but this time a very large amount. And let me show you, come over here, and I'm going to show you the liquid nitrogen. We actually have it in a large container here. I'm just going to transfer some of it. Again, it looks just like water, but it's minus 196 degrees Celsius. So it's not water. Let's bring this over to the demonstration area. Set this over here. Dave, how's that water coming?
It's coming along.
Are you watching water boil?
I'm watching water boil.
Okay. So I'm going to take the liquid nitrogen and I'm going to pour it into the vat. Dave is preparing some boiling water for me. And the two of us are going to explain things. I think you can hear Dave.
A bit of a train interruption.
So liquid nitrogen is boiling right now. And Larry, why don't you show the audience what that looks like?
Ah, yes. There's quite a lot in there.
And you see that there's some vapor above it. Dave, what's that vapor?
So we basically have a vapor forming of that liquid nitrogen. Is actually forming a vapor barrier as it warms up a little bit. So we have some nitrogen right there.
But is that what's visible, or is it the water?
It's the water vapor in the air that we're actually seeing.
Okay.
And that's similar to what we do when we look up in the sky and see those pretty clouds, right? We have water vapor in the air and clouds over there. And clouds over there, and that's what we'll see when we see that water vapor in the air.
Okay.
But you know, why does that cloud form, Boris? What do we actually get when we get a cloud formation?
Well, the clouds are made up of water vapor and ice crystals.
Right.
Okay. And so what we could do here is we can actually demonstrate the formation of a cloud by taking water and suddenly turning it into a gas, but then immediately cooling it down. So what happens in the air is water vapor starts to come together,
right?
And then it cools, and when it cools, it condenses into water droplets, and some of that condenses down into...
And that's what we see then.
And then that's exactly what we see.
Okay,
Those ice crystals in the water droplets.
So if we want to create a ground cloud, we're going to have to change the temperature of water very quickly.
Yeah.
So if I can give you some boiling water...
Boiling water is key because boiling water is right at the point where it changes into a vapor.
There you go. Okay. And how do we cool it down very quickly? Well,
liquid nitrogen.
Liquid nitrogen.
Exactly.
Don't you have to prepare something to get yourself ready for this?
You know, just for safety?
Let's do that.
Yeah,
Let's do that.
So let me get ready. So as you can see, this is going to produce a rather large cloud. Well, that wasn't good. Dave, I think I dropped one of the gloves into the vat. So, so you're going to give me one of your mitts. Okay. Okay. We'll do it that way. We're probably close enough?
I think so. I have some steam rising off the top. So I'm going to go ahead and turn this burner off.
So Dave's at the stove right now, an outdoor stove, bringing over the boiling water. You can set that on the floor, and then you'll give me one of your gloves. The white glove I need. And so what we're going to do is we're going to use the water to turn We're going to use a liquid nitrogen to turn the water into a cloud. But you have a face shield. I should cover my face. Okay. Are we ready?
We are ready.
Okay, count down, Dave.
3, 2, 1. Oh my goodness. We hope so much that you enjoyed. Besides the technical difficulties that we had earlier, we hope you really enjoyed our science, physics, and chemistry is everywhere demonstration show. Horse Law, anything to add to the audience?
Keep studying and enjoy physics, and look for science everywhere. Thank you very much. So long.